Hello, so in this video we will see how to do the implementation of a singly linked list, okay? And I will try to explain everything step by step, so it will take a while, okay? Um, okay, so let's see the definition of a singly linked list from Wikipedia. And it says here that the singly linked list contains nodes which have a data field as well as a next field, which points to the next node in line of nodes. Operations that can be performed on singly linked lists include insertion, deletion, and traversal. Okay, and we have here an example of a singly linked list. These are nodes. Okay, every node have a value. Okay, and every node have a next, and the next is pointing to another node. Okay, this node is have a value that is 99 and is pointing to the next node, and the next node have the 37 and is pointing to nothing. Okay, this is the end of the singly linked list. Okay, so the idea here is to do that here in Python. Let's start. So let's define the class node. Okay, and this class, like every class, has an initializer, and it receives the self, and a value. Okay, and let's say that it has a property that is called value and is equals to the value, and it has another property that is the next, and it is equals to none. In the beginning is none. Okay, so this is the most basic structure of a singly linked list. Okay, a node. With this, what we can do with this structure, for example, let's create here a list L that is equals to node. Okay, and in the Wikipedia example they start with the number 12. Okay, and they say also that the next is equals to the node with 99. So let's do that. L.next is equals to a new node with the value 99. These new nodes with the value 99 have a next with the value 37. So let's do that. How to do that? We do L.next, we are pointing to this guy. Okay, and since it is a node, it has a next, so .next, and we do node 37, I believe, 37. If we want to print these, we can do directly like L and print L.next and print L.next, and let's see what this does. Let me move up and let's run, and we get the address of three objects. Okay, they are different. So let's define a pretty print. For that, we need to define in the node class the underscore str for string and underscore. So is toString. Okay, to simplify the thing, we must define the toString, and is very simple. We just need to return a string, and I will create here a fString where I select the element, the value. I usually call this property as elements. Okay, that's why I was making a mistake, but I didn't. So with this simple adjustment, if we rerun, we get now the values 12, 99, and 37. Very cool. Okay. If we want to add another element, another node, we have to do l.next.next.next, okay, because is the next of this guy, okay, and to reach this guy we have to do this. We are traveling through our chain of nodes, okay, and let's put here a 4, and if we want to add another one, let's say 5, we have to do next, okay. And you already, I believe you already see where this is going. This is not very user friendly, because for example, if we have 100 elements in our list, it will be l.next.next.next.next until it reaches the next that is none, and then we can insert. So this is not very user friendly. By the way, we can simplify these, okay? We can simplify these. Let's define here a node that is equals to L, and while the node is different than none, we want to print the node, okay? And we want to update the variable n. So the n will be pointing to n.next, okay? We are traveling through the chain, and if we run these, we will see all the values, okay? 12, 99, 37, 4, and 5, okay? Okay, so what to do next? Like I was trying to say, this is not very user friendly, and that's why we will create a class that we will call singly linked list, okay? This class will manage this, okay? It will manage the insertion of new nodes. It will manage the way we access a specific index of our singly linked list and remove elements from the list and so forth, okay? So like any class, it has a initializer. It will receive the self, and it will have a field that is the add, and for now the add is none, is nothing, okay? The idea of the add is to point to the first element of the chain of nodes, okay? Okay, what's to do next? Let's say with this structure, and without creating too much things here, we can do a simple thing, that is create a single linked list that is equals to singly linked list, and let's say that the singly linked list dot add is pointing to our chain of nodes, okay, to the L. And what we want to do next sorry, is to be able to do a print of our single linked list, okay? Like I said before, the main idea of the class single linked list is to handle the things, the heavy stuff. We will not handle these for now, okay? We will handle the pretty print, like we did in the node, okay? Here we have to define a toString method, okay? Let's do that. Let's define underscore toString or str. It receives the self, and it will have to return let's define here a result that is an empty string, and it will return the result. Okay, in the middle we will do the magic. So we have add. Let's define n that is equals to self.add. Okay, and we will do exactly the same thing that we were doing in the while loop. So while n is different than none, okay, we want to result plus equals to fstring, and let's provide the n. The n is the node, okay, the n is the node, and the node already have a toString, okay, so it will print the value of the node. What more? And also we want to add a comma and a white space. Okay, so we have to update the nodes, okay, to the next node. So n is equals to n dot next, okay, until it reaches the one that is none. So it will stop this while loop and it will return the string with the result. And let's see if this is working. Let's run, and now we get this, okay, 12, 99, 37, 4 and 5. As you can see, we have here a comma, and you cannot see, but we have a white space. So we must remove that thing, okay, we must remove that thing from the result. Let's say that the result is equals to reassign the result, and is equals to all the chars of result except the last two, okay, -2. Okay, so is running and is perfect, okay. So we are already handling the singly linked list, sorry, is already handling the pretty print of the linked list, okay. But we want more from this. So in the next part we will define, we will do the addFirst, okay. It receives the self, of course, and a value, and for now we just pass. It will have also addLast, okay, receives the self and the value, and for now we just pass. And it will have just to be different, insertAt, and it receives the self. It receives an index because we want to insert at a specific position, and a value, okay. And for now we just pass, okay. So the next step will be doing this, the addFirst, okay. So let's do the addFirst, okay. And to simplify this, I will change this a little bit. We want to add the number 1, 2 and 3, okay, 1, 2, 3, 4 and 5. And let's think about the addFirst. Okay, let's go here and let me show you something. We have the linked list have add, okay, and let's put here also a none, okay. And in the beginning our singly linked list is pointing to none. The add is pointing to none, okay. And the idea is to create a new node. I will simplify the nodes, so it will just have the value, okay, here, but it has a next, of course. It has a next, and the idea is to the add to point to this guy. So let's do that in the addFirst. Let's do that. The first thing that we want to do is create a new node, okay, the node, and it will receive the value, and then we want to self.add, will be pointing to this new node. Okay, new node. So what we are doing right here is exactly this. Okay, let me delete this row. We are doing exactly this. But now let's imagine that we want to add another node. Okay, our singly linked list have at this moment one element, but we want to add another element, the number 2. So the idea is we must connect the add with the first element, because this is the add first, and we want to connect the element with the previous first element of the list, this one, and of course this connection will disappear. Okay, so let's do that. First, our addFirst is creating the element, the new node. In this case is the number 2. Okay, and then we are assigning to the self.add the new node. So we are doing this connection and we are destroying this connection. This is a problem. This is a problem. We cannot do this in this order. We first have to connect the new node with the element that the add is pointing to. Okay, this is important. So let's do that. Before doing this, we have to say that the new node dot next is equals to self.add. So the next is the element, the node that the add is pointing to, and after that we can update the add. So we can create this connection, and when we create this connection disappears. Okay, and we are doing exactly that in this line of code. Okay, this is a little bit confusing. It will get even more confusing, so prepare yourself. Prepare yourself. Okay, we are ready to test this. So instead of doing all of these, we can simply, and let me remove these, we don't need these anymore. We can do singly linked list addFirst, and we provide the number 1. Let me duplicate these and provide the number 2, the number 3, the number 4, and the number 5. Okay, and we don't need these anymore. So you see, this is better than the previous code. Okay, let's see if this is working. Let's run this again, and we get 5, 4, 3, 2, and 1 reversed. Why reversed? Because we are adding first. So every time that we add an element we call addFirst, it is creating a node, is white, it is creating a node, okay, the number 3 for example, it is connecting to the previous next, the previous first element of the list, it is destroying this connection and connecting the add with the first element, in this case is the number 3. The next one will be the 4, it will go here, okay, 4. My drawing skills are not very good, sorry. And is doing this, okay, is connecting with this guy, and the number 5 is the same thing. Okay, so this is it. This is it. Next, we are not finished with this addFirst, okay, but for now we are finished. We are finished. So the next thing that we want to do is the addLast. So see you in the next part. So let's do the addLast. And well, the idea of the addFirst is to add in the beginning of the linked list, and the idea of the addLast is to add the elements the nodes to the end of the linked list. Okay. Okay, so let's go here to our drawings, and in the beginning, in the beginning I didn't have this selected again. In the beginning, the add is pointing to nothing, to none. Okay, and what we want to do, again, we want to create a node, okay, with the number 1, for example, and we want to break this connection and connect the add to the new node. Okay, so let's do that. Let's go here to the code and first create the new node is equals to node, and we provide the value. Okay, and then we say self.add is pointing to the new node, and this is for the case where we have an empty list. Okay, so we at this moment we have this. Okay, add that is pointing to a single element, but we want to add more elements. We want to create more nodes. We want to create a node with the number 2, for example, and in this case is a little bit different from the previous method, the addFirst, because we just want to create this connection. We don't want to update the add. Okay, we just want to update the to update the next of the first element in this case, and then for example, when we add another element, the number 3, what we want to do, again, we want to update the next of the last element. Okay, so I said here that is the first element, but when a linked list have just one element, the element is the first and also it is the last. Okay, so the idea is to connect the last element to our new node. Okay, so we have here 2 scenarios. The first scenario is when the linked list is empty. So if the self.add is pointing to none, this means that the singly linked list is empty. So we are adding a new element to the singly linked list. In the other cases, when the singly linked list already have an element, what we actually want to do is to travel in the chain of nodes. Okay, for us to be able to connect the last node with the new node to make this connection. Okay, so let's do that. Let's go here and let's declare an n that is equals to self.add. Okay, and while n.next, okay, is different than none, we want to travel in the chain, so n is equals to n.next. Okay, we update the n. When we reach this scenario where the n.next is actually none, it means that we are in the last element of the chain of nodes. So what we want to do, we want to say that the n.next is equals to new node. Okay, is just this. So what we are actually doing is, let me put here, I'm almost over the image. Yeah, now is good. So for example, we are adding the number 5 and we travel from from this position, and then we go dot next, n is equals to n dot next, and then n is equals to n dot next, and n is equals to n dot next. And in this case, the n dot next is pointing to none. Okay, so we are creating this connection. So n dot next is equals to the new node. Okay, and we are good to test. We are good to test this. Instead of using the addFirst, we will use the addLast. Okay, and let me replace these guys with these. Okay, let me open the terminal and run, and now we have 1, 2, 3, 4, and 5 in the right order because we are adding last. By the way, let's print the add just to be sure that everything is okay. So to print the add, we go to the definition of the toString of the singly linked list. Okay, we go here. Let me hide this so you can see everything, and let's add here to the result. Okay, plus equals fstring. Let's put here a pipe, and let's say here head, and let's say self dot add. Okay, let's print the add, and let's run this again, and now we see the add. The add is the number 1, the node with the value 1. Okay, and we could say that we are done with this. Okay, but we can simplify this code. Actually, we can simplify this code because many implementations of singly linked lists have a add, but also they have a tail. Okay, they have a tail, and the idea is the add is pointing to the first element of the chain of nodes, and the tail is pointing to the last element of the chain of nodes. Okay, so because of this change, we have before going here to the addLast, we will update the addFirst. Okay, because we have to see if the self.add is equals to none. It means that the singly linked list have 0 nodes. So this is the first node that we are adding to our singly linked list, and the first node, like I said before, the first node, when the singly linked list have just one node, is the first one and the last one. So it means that self.tail is equals to the new node. Okay, we are creating the connection with the tail. So let me go here and add a tail, and let me put here the tail. This is confusing now, but we can remove all of these. We don't need these anymore. And in the first case, when we are adding first, we are creating the first element. Okay, and it is pointing, the add is pointing to this guy, and the tail is pointing to this guy. Okay, next we have to see the addLast, because since I said before, we can simplify the code. So I will comment this code. Okay, and since we have a tail, and just to remember you, the tail is pointing to the last element of to the last node of our linked list, we can do self.tail. Okay, self.tail sorry, let me create here a new thing. Okay, we are creating, and self.tail.next is equals to our new element. Okay, self.tail.next is equals to the new node. Okay, we are creating this connection. Okay, and after that we must update the tail. Let me put here. I'm very bad drawing. We must update the tail to point to the last element. Okay, so tail dot next is tail.next is equals to the new node. Okay, is what we are doing here. And next we want to update the tail, so tail is equals to the new node. Okay, after all of these we have to say self.tail is equals to the new node. Okay, as you can see, this is very confusing, and if you don't use these drawings it will be difficult to get into this code. This is true for the if and the else statement, this instruction. So we can do this. Okay, we can do this outside. Let me remove this from here and put here. Okay, because we want to update the tail like we update in this case. Okay, if we are adding last when the linked list is empty, we want to update the add and also the tail. Okay, we are ready to test. And before testing, let's update here the toString of the singly linked list. Okay, the toString, instead of just displaying the add, we also want to display the tail. So tail self.tail. Okay, so we are ready to test. We are already adding last, so, and because we changed the addFirst, let me put here the tree, the addFirst in the tree. So the number 3 will be the first element of our list, and the result is this. We have the number 3, 1, 2, 4, 5, and the add is the number 3, the tail is the number 5. Okay, and apparently everything is running as expected. Oops, it's not this, it's this. Okay, 1, 2, 3, 4, 5. The add is 1, the tail is 5. Okay, so we have the add first, we have the add last, and in the next part we will do the insert at. So see you there. Let's do the insert at. And the insert at is a little bit different because we have here an index. We want to insert the element at a specific position of our list, and we have here a problem because we don't know how many elements are in the list, and the index must be between 0 and the number of nodes that we have in the list. So let's count. Let's declare here a size that is equals to 0. Let's declare an n that is equals to self.add. Okay, and let's do here a while loop to travel in our list while n is different than none. What we want to do, we want to count, so size is plus equals to 1, and also n is equals to n dot next. So at the end of this while loop we know how many elements are in our list. Okay, so the next thing that we want to do is have the guarantee that the index is between 0 and the size. of our list. So if 0 is less or equals than index and the index is less than the size of the list, in other words, if the index is between 0 and the size exclusive, okay, we want to add something to the list. And now we can take advantage of the previous two methods that we did, because if the index is equals to 0, it means that we want to add at the beginning of the list. So self.addFirst, and we provide the value. Okay. In the other hand, if the index is equals to the size, this means that we want to add at the end of our linked list. So self.addLast, and we provide the value. It's just that. Else, if we want to insert the element somewhere between the first element and the last element, we have to do other things. We have to think a little bit more. Before going here, I want to call your attention for this, because in this case we have to do this. Okay, let me show you why. Because, for example, if we have three elements, okay, this is the index 0, index 1, and index 2. They are 2. Is not a very good 2, but you understand. They are connected, and let's say that we want to add an element to the end of the list, so we must provide the index 3 to our function. This index must be 3, and if we say that index must be less than the size, less than 3, it's not valid and we cannot add, so we must include the size, and with that we are able to add the fourth element, okay, at the end. Okay, so we are here. We want to add something in the between the first and the last element. Let's say first, of course, we must create our new node that is equals to node, and we provide the value. Okay, and then let me show you. Let's imagine that we want to add an element in this position in the index 2. It means that we must connect this guy with the new node, and this one will connect to this one. Okay, for us to be able to do that, and don't forget this, the head is pointing to the first and the tail is pointing to the last. To do this, for us to be able to do this, we must travel from the beginning of the list to the previous element, the previous index where we want to insert. Okay, so let's do that. Let's declare here a previous that is equals to self.add, right, and sorry, while index -1 is greater than 0, we want to travel, so previous is equals to previous.next, and also update the index minus equals 1. Okay, with this code we have the guarantee that we are in the previous element of where we want to insert. Okay, this only works, by the way, this only works if we have at least 2 or yeah, 3 elements in our list, and that is true. Why? Because we know that the index is between 0 and the size. Doesn't matter how much is this size, okay? And then if we are in the else statement, it means that this is false and this is false. And what this says to us? This says that, well, we are not trying to insert at the index 0. Okay, so at least we have 2 elements if this test fails, and if this test fails, it means that at least we have three elements. Why? Because it's not the index 0 and it is not the index 1. It is other index, okay? So when we go here to the else statement, we know at least that we have 3 elements in the list. Okay? 3 nodes. Okay. I hope that you understood. I tried my best. So, again, imagine that we are in the previous. Okay, we are in the previous. Let me put here a previous for you to see it better. Previous. Okay, so we have a previous that is pointing to this guy, right? And now we want to connect this guy. We want to connect this guy to this guy, and this guy, the new guy with this one. But the order here is very, very important, because if we connect this one with this one first, it means that we are breaking this connection. So it means that we cannot access the rest of the list after breaking the connection, and it means that we are not able to do this connection. Okay, so first we must create this connection, and this means that the new node dot next is equals to the previous node dot next. Okay, this guy. So previous dot next. Okay. Next, we want to connect the previous with the new node, right? So previous dot next is equals to the new node, and making this connection we are breaking this. So let's go here. Previous dot next is equals to the new node. Okay, let me adjust here the code. Okay, yeah, we are done with this. Now we can test. Let me duplicate this, and let's say that let's print. No, sorry. Let's do a SLL, and let's insert at index 0. Let's insert at the beginning the ABC string. Okay, and let's see if this is working. So let's run. We get this. Okay, the add is now ABC, and we have this tail. Let's insert this at the index 0, 1, 2 at index 2, so it will replace the, it's not replace, it will be in the position of the number 3. Okay, and let's add to the last, so 0, 1, 2, 3 and 4. So we want to insert at index 5, and is at the end. The tail is now ABC. Okay, but we are not done with this yet. We are not done with this yet, because this code, well, you see, many singly linked lists implementations have adds, they have tails, and also they have a size that is equals to 0 in the beginning. Okay. By the way, let's update here the toString to show the size. Result is equals to plus equals f string, and we put here a pipe, a size, and self dot size. Okay. Sorry. The toString is updated. Then we must go here to the first, add first, and of course, since we are adding a new node, self.size is equals to plus equals 1. Okay, we are adding up. The addLast is the same story. Self.size plus equals 1. Okay, here we don't need these anymore. I will just comment. Okay, now we can call self.size and here self.size. And don't forget to, in the else, just in the else statement, we want to self.size plus equals to 1. Okay, that's it. We don't need to do outside, because is not, we can't do outside of the else. Okay, we can't do like this, because of course at the addFirst and addLast we are already updating the size. Okay, so it must be inside of the else statement. Okay, let's see if this is still working. Is still working. Now we have here the size, we have the ABC is the tail, and the size is now 6 elements. 6 elements. Okay, so our singly linked list is now a little bit more useful, right? Is a little bit more useful, but we want to make even more. So next we will do remove-first, because we want to remove elements from our linked list. For now is we just pass. We want to define a removeLast and receives the self, and for now we just pass, and we want to define the to be different remove the entire removeAt, and we receive the self and the index, and for now we just pass. So this means that in the next part you will see how to do the remove-first. So see you there. Okay, let's do the remove-first. Okay, so the idea when we remove a node is that we remove from the list, and also we return that node. Okay, so let's declare here a result that is equals to none. Okay, and at the end we return the result. In the middle we do the magic for the thing. So we just want to do something when the list have at least one element. So we do here a check if self.add is equals to is not none, we want to remove something from the list. Okay, so let's go here to our drawings, and let me put here one node. Okay, and the add is pointing here, the tail is pointing here. We don't need the previous. we need a result. Okay, so the idea first is we want to point the result to this element. Okay, we want to point to this guy. So let's say result is equals to self.add. Okay, and then we have here two situations. Okay, if the linked list have just one element, the add and the tail will be the same. Okay, will be pointing to the same place. So if self.add is equals to self.tail, it means that we have just one element, and for now we just pass, and the other cases we will do here. Okay, if that is true, if the adds and the tail are pointing to the same node, what we want to do, we want to break these two connections, so they will be pointing to none. Okay, so let's do that. So self.add add is equals to none, and self.tail is equals to none in the case that we have just one element. Okay, in the list. In the other scenarios, what we want to do, in the other scenarios, let me clear these, and let's say that we have here another node and another node, and they are connected like this. The tail is pointing here. Okay, and we want to remove this guy. The result is already pointing to this guy. Okay, is okay. Now what we want to do, we want to break this connection to connect the add to the next. So add.next, sorry, self.add is equals to self.add.next. Okay, so self.add is equals to self.add.next. So we are pointing to the next element, and then we just deleted this connection, and we have one more thing to do. We want to break this connection because this element doesn't belong anymore from this list. Okay, so we do result.next is equals to none, and that's it. We could do this outside, but since in this case we have just one element, the result, the only element is pointing, the next is pointing to none already, so we don't need to do outside. Okay, and because we are removing something, because we are removing from the linked list, we cannot forget to self.size minus equals to 1. Okay, update the size. Okay, and that's it. I think is done. Let's test this. Now let's test these. Let's say here, let's print the element that is removed, sll.removeFirst. Okay, and then we want to print the SLL. Okay, and let's test this, and we removed, this is the list. Okay, we removed the first one, it had 6 elements, and now it has two. It don't have the element with the value 1, and the size is 5, and the add is of course 2. Okay, so this is working. Apparently this is working. Let's do some more tests. I will remove these prints. We don't need these anymore. Let's run again, and it removed the 1, the 2, the 3, and the list now have 4, 5, and ABC. The add is 4, the tail is ABC, and the size is 3. So it is working. Okay, so we are done with the remove-first, and in the next part you will see how to remove last. Okay, let's do the remove last. Okay, so let's declare a result that is equals to none, and let's return the result. In the middle we do the magic. If self.add is different than none, it means that the linked list is not empty. Okay, so let's go here to our drawings, and at least we have one element. We have the add pointing, yes, we have the add pointing to this guy and the tail pointing to this guy. And what we want to do, we want to point to this guy, to the tail, okay, where the tail is pointing to. Okay, so the result is equals to self.tail, so where the tail is pointing to. Okay, and then we have here a situation, because if the self.add is equals to the self.tail, it means that our linked list have just one element. Okay, and what we want to do is this situation, we want to break these two connections. Okay, so self.add is equals to none, and self.tail is equals to none. Okay, else when we have more elements, let's go here to the drawing. Let me reverse these, and let's reverse these two, and also these. Okay, let me make here more nodes so we can see everything. Okay, the tail is now pointing here. They are connected, as always. They are connected, and our result is already pointing here to the tail. Okay, to the node where the tail is pointing to. Okay, and what we want to do, well, we want to go here to the previous, so our previous will point to the add. Okay, and it will navigate till it finds the previous element of the element where the tail is pointing to. Okay, this is confusing, but you will see how it is. Self is equals to add. Okay, the first step. We are pointing here to the head, and now we want to navigate through the chain. So while the previous dot next is different than self.tail, we want to previous is equals to previous dot next. Okay, so with this code we are going to these nodes. Okay, while the previous dot next is different to the node where the tail is pointing to. Okay, so these don't exist anymore. Let me remove this. Okay, and let's point to the right place. So the previous is pointing here. What we want to do next, we want to break this connection, right? And we want to point the tail to this new last element. Okay, so previous.next will be equals to none. So previous.next is equals to none. Okay, so we already deleted this connection. And next, we want to delete this connection and make the tail equals to the previous. So self.tail is equals to the previous. And that's it. That's it. We don't need to do anything else except one thing. Of course, we want to self.size minus equals to 1. Okay, update the size. Update the size. Okay, I think is okay. Let's test. Let's test. Remove last. Remove last. Let's remove here last, last, and last. Okay, let's open the terminal. Let's run, and yeah, we have here the original list. We remove the ABC, the number 5, the number 4, and we have now a list with 1, 2, and 3. The add is the number 1, the tail is the number 3, and the size is 3. It has 3 elements. Okay, so it is working. It is working. So after doing the remove last, we will do the last one, removeAt. Okay, see you in the next part. Let's do the last one, the removeAt. So the idea is the same. We want to return what we remove, but in this case we want to remove in a specific index. So let's declare a result that is equals to none, and let's return the result. In the middle we do the magic as always. So if self.add is different, this is different. The idea is to remove at a specific index. Okay, so if the index is between 0 and the list size, we want to remove is a valid index. So 0 less and equal to index, and index is less than self.size. And attention, this is just less, okay, not less or equal, because the index starts at 0 and the size not. Okay, and now, like we did in the insertAt, we can take advantage of the fact that if the index is 0, we want to result is equals to self.removeFirst. Okay, and else if the index is equals to the self.size minus 1, the last position, the result will be equals to self.removeLast. Okay, and then we have the other scenarios that we have to go to the drawings again. Okay, let's put here, let's say 1, 2, 3, 4, maybe another one. Oh, my drawing skills are even worse. But they are connected. We have here the tail pointing to this guy, the head is pointing here, and again, if we are in the else statement, it means that we are not removing the first and not the last one. Okay, let's imagine that we want to remove the goal is to remove this one. Okay, No, let's remove here because you can get confused with this. Okay, let's remove this one. So the idea is again to point the previous to the add, okay, and then we will navigate to the next one till we get the previous index where we want to remove. In this case is this guy. Okay, let's do that. So, oops, let's declare a previous that is equals to self.add, and let's do a while loop while the index -1 is greater than 0. We want to update the index, okay, minus equals 1, and also we want to update the previous to be previous dot next. Okay, we are traveling in the chain, so here when it goes out, when the while loop ends, it means that we are in the previous. Okay, so here we want to say that the previous dot next, the result will be equals to previous dot next. Okay, so we want to point the result to this guy. Let's do that. Result is equals to the previous dot next. Okay, first part is done. Then we want to connect the previous dot next with the previous dot next. Okay, we want to make this connection. Okay, and with this we are breaking just this. Okay, so previous dot next is equals to the previous dot next. Okay, previous dot next is equals to the previous dot next. Okay, and one last thing that we must do is break this connection. So result dot next is equals to none. Let's do that. Result dot next is equals to none. Okay, let me put here the code aligned. Okay, and that's it. The last thing that we want to do, and inside of the else statement, okay, because the remove_first and the remove_last already do that, is to update the self.size with -1. Okay, okay, and that's it. I think is done. Okay, let's do the removeAt. Let me remove this. removeAt index 0 for test. It is working. Okay, it decreased the size. Let's remove at 5, so it will remove the ABC. I think yes, it just removed the ABC. And let's remove at 3, so 0, 1, 2 and 3. It will remove the number 4. Okay, and we got this. We got the number 4, 1, 2, 3, 5 ABC. The add is 1, the tail is ABC, and the size is 5. Okay, is working. Okay, is working. Okay, so this was the last exercise for this. Well, maybe I can do a bonus thing. Let's say that we want to do this. We want to access by index, elements by index. How to do this? You will know in the next part, okay? So let's do the indexing, and this is actually very easy to do. Let me show you. Let me remove this extra space, collapse these, and here in the singly linked list we can define here underscore underscore get item, okay, and underscore. It will receive the self and index, okay, and we want to declare a result that is equals to none. We want to return the result, and again in the middle we will do the magic. And if the index is between 0 and the index is between the self.size, what we do result is equals to self.add, okay, and then we travel in the chain of nodes. So while index is greater than 0, we want to update the result to be equals to result.next, and update the index, so index minus equals 1, okay, and that's it. That's it. Let's see if this is working. So let's run, and we got the number 4 in the list. Let me put here a string. Sorry, it's not here, it's here. Indexing, and we got the number 4. Let's provide the number 0. We got the number 1. Let's say 6, index 6. So we get none. Okay, index 5. We get ABC is the last element of our linked list. Well, you could do something like this, but it will not work because the code is not prepared for this, because this returns a slice, okay? And I will not do the code for that. But I will give you the keys for that. So if the type of the variable that I called index is a slice, we want to do something, else we want to do this, okay? And what we want to do, I want to show you what is a slice. A slice is something that have start, okay, so index.start, it has a stop. Oops, let me give a space here. It has a stop and index.stop, and also it has a step, and let's put here index.step, okay. So let's run this again, and we get none. Is not entering in the thing. Why? Oh, no, is entering. Sorry. Sorry. We have here 1. The start is have the value 1, the stop have the value 4, the values that we have here, and it has a step with the value none, okay. If I put here 100, the step will be 100, okay. So this is it. I hope that you learned something from this video, okay, and thank you for watching. if you want to help this channel, please leave likes, share with your friends. This is very important, and social media. Um, Leave a comment. If you can, um, make a donation, because I'm trying to get some money to buy a better microphone. And if you like even more, if you like even more, you can become a member of the channel by clicking on the join button. Okay, so um, thank you very much for watching this video, and let see ya in the next video. Okay, bye.